Hi, my name is Jack Walton, and this is my report on Lab 4, Macroscopic View of DC and RC Circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, as well as to use multimeters to measure the actual values of conventional current and potential difference in circuits, as well as to examine the behavior of ohmic resistors and capacitors. In order to complete this lab, I simulated different circuits using Circuit Construction Kit with various resistors and capacitors. And our results of part 1 is that the sum of potential difference across the circuit is equal to 0, and the resistor is not a perfect resistor, so the resistor's values are not exact. And the results in part 2 is that RC is equal to 5.99. The main physics concepts used in this lab is the conservation of energy, which uses the loop rule, which states that for a complete loop, the potential difference overall is equal to 0. The conservation of current, which uses the NOPE rule, which states that the overall current going into a point will equal the overall current going out of that point. Ohm's law, which states that V voltage is equal to I times R, or current times resistance, and the difference between parallel and series circuits, as well as how resistor capacitor circuits work. So in part 1, I predicted that I1 and I2 would equal 0.02 amps using the loop rule, and the given values R1 and R2. To solve this, I form the equation 0 equals -2 times 1.5 volts plus change in V times R1 plus change in V times R2, and I just solved for V. And then I created the circuit and measured the current to show my predictions were correct. After reversing the ammeter, I got the same readings as before. After replacing one ammeter with a voltmeter, I got the readings of 0 volts and 3 volts. And you can see the circuits displayed on the right side. So on the right hand side, you can see our circuit, the diagram of our circuit, and then each point along the circuit between the resistors, capacitors, and the two batteries. And so those points, the potential difference between each of these points is displayed on the left. And this all makes sense because when all the potential differences are added together, they sum to 0, showing that the potential difference across the entire circuit is 0. And the bottom picture on the right shows the graph of potential difference, showing how it increases as you hit the batteries, and then over time across the resistors it decreases down to 0. Furthermore, using the current and potential difference measurements, I was able to calculate the actual resistance of each circuit element. Resistance of 47 is actually equal to 47.95 ohms. R100 is actually equal to 102.5 ohms, and the resistance of the wire is equal to the resistance of the ammeter, which is 0 ohms. And the calculated resistances are not exact because there is no such thing as a perfect resistor. It makes sense that the calculated resistance is higher because there is an extra resistance due to extra resistance in wires, other circuit elements, and any imperfections in the resistor. For part 2 of resistor capacitor circuits, you can see our initial circuit on the right displayed, and when the light bulb was connected to just the battery, it glows very brightly. When the light bulb was connected to the capacitor and battery in series, it slowly dims as the capacitor is charging. When the light bulb is connected to the capacitor only, it also dims as the capacitor is using its charge. The higher the resistance of the bulb, the longer it takes for the capacitor to charge. Here on the right, you can see the circuit with the capacitor now added, and with a 10 ohm light bulb, it took 10.85 seconds to charge the capacitor and 10.89 seconds to discharge the capacitor. With a 20 ohm light bulb, it took 18.33 seconds to charge the capacitor and 18.57 seconds to discharge the capacitor. So we use time dependence to graphically display the charging and discharging of the capacitor. So we set up the circuit with a 30 ohm bulb connected to the charge capacitor, measured the initial potential difference, which is -9 volts, recorded 20 seconds of time versus voltage data, calculated the potential difference over the initial potential difference, plotted natural log of the voltage over initial voltage versus time, and then the slope of the graph is equal to -1 over RC, or just the inverse of RC, and the negative inverse of RC, and therefore RC is equal to -1 over -1.67, or 5.99. You can see all of our data on the left side, and in the middle is our graph of the natural log over time. So some concluding questions. What if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? A real ammeter has some small amount of resistance in it, so its readings would be slightly smaller. What if you were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. The model would predict that the capacitor would reach full charge faster than it actually would in real life in a real life scenario. Because in a real life scenario, the wires have some resistance in them, and therefore the capacitor would take longer to charge because the time is proportional to the resistance of the circuit.